Hi, and welcome to section 6.6 where we solve exponential and logarithmic equations. We're going to start solving exponential equations using a method of like basis and another method of using logarithms. Then we're going to be solving logarithmic equations by using the definition of a logarithm and also the one-to-one property of logarithms and other properties of logarithms to solve them. All right, let's get started. Exponential equations are equations that contain the variable in the exponent. One thing that is helpful for exponential equations is that exponential equations are one-to-one. So if we know that if b to the y equals b to the x, it must be that y equals x, since these equations are always increasing or always decreasing. So here is where we're first method of solving exponential equations are solving exponential equations that have like basis. Let's do the first example. 5 to the t equals 125. When you first look at this, you might not think these have like basis, but they do, because 125 can be written as 5 cubed. So if we rewrite this, 5 to the t equals 5 cubed, we can see that t must be equal to 3. Again, in part B, we can write 64 as a power of 2. 2 to the w equals 2 to the, I think, 6th. Let me just double check that. Yep, 2 to the 6th. So w is equal to 6. And finally, one last problem that's a little bit more complicated. We can write 3 to the 2x plus 1 equals 3 cubed, since 27 is 3 cubed. This tells us that 2x plus 1 must be equal to 3, and we solve this equation. Subtract 1 from each side, 2x equals 2, divide by 2, x equals 1. We can check our solution to this one. It's a little more complicated and it's good to check. 3 to the 2 times 1 plus 1 equals 3 to the 3, which is in fact equal to 27. So if you have an equation where you can write both sides as the same base, you can use this property to solve those exponential equations. But what happens if we don't? What if we have something like 5 to the v minus 3 equals 137? 137 isn't a power of 5, so we're going to have to learn a new technique to solve these types of exponential equations. We're going to use logarithms to solve exponential equations, and in particular, we're going to use this property of logarithms, the exponent property. If you have log of m to the p can come down in front and become p times log m. This is how we're going to get the variables out of the exponents. Let's do an example. So let's take the logarithms of both sides of our equation that we tried there. Log of 5 to the v minus 3 equals log of 137. Since logarithms are one-to-one, we can take logs of both sides and maintain the integrity of the equation. Bring down the v minus 3 using our exponents property. V minus 3 times log 5 equals log of 137. This equation might seem a little weird to you right now because you're not used to looking at logarithms. But remember, logarithms are just numbers. So log of 5 is just the number you put on 10 to get to 5. And it's just, in fact, we can even plug it into our calculator and get a decimal approximation. Oops. It's about equal to negative 0.77, but it's just a number. And so we can just treat it like a number to solve these equations. If this was just 5 times v minus 3 equals 137, we would just divide off 5. So we're going to do the same thing with log of 5. Divide it off. Treat them like numbers. They are numbers. This gives me v minus 3 on the left-hand side, since these cancel out, equals log of 137 over log of 5. And now to find v, I just need to add 3 to each side. I'm just going to actually skip to that. V plus 3, and I get v equals log 137 over log of 5 plus 3. And this is your final solution. That is your exact solution, and that's the answer you want to put in if they asked for exact solution. I think it's helpful when I'm checking solutions to logarithms if I can use a decimal approximation. So I'm going to use a decimal approximation to check, but that's not the answer that I'm going to give. So to check, I use a decimal approximation. So let's get a decimal approximation by v by plugging in this into our calculators. So I'm going to take log of 137. I'm going to divide it by log of 5. And to that value, I'm going to add 3, and I get v as about equal to 6.057. I'm going to use that to check my answer. I'm going to take 5 to the original equation, right? 5 to the 6.057 minus 3, and I hope I get something close to 137. Sure enough, I got 137 with a lot of decimals when I used a lot of decimals for my v-value. Sure enough, that equals 137, and we got the correct answer. All right, let's try another example of this one. Same idea. This time we're going to use the natural log. The reason I'm choosing to use the natural log is because this equation is base e. So if I use natural log with base e equations, so I'm going to take the natural log of both sides. Natural log of e to the 4x minus 7 equals the natural log of 11,243. My property of log still works, and I get 4x minus 7 times the natural log of e equals the natural log of 11,243. Natural log of e is really just equal to 1. Remember, e to the 1 equals e. So the natural log of e equals 1, so I can replace that with 1, and then this side becomes 4x minus 7 equals the natural log of 11,243. Proceeding on to solve this linear equation, remembering natural log of 11,243 is just a number. Add 7 to each side. 4x equals natural log of 11,243 plus 7. Divide both sides by 4, and there's my exact answer. X equals the natural log of 11,243 plus 7 all over 4. And again, that is my exact solution that I would put into for my answer. To check, I'm going to go back and use a decimal approximation. Check over here. All right, let's get a decimal approximation in our calculators. X is about equal to natural log of 11,243 plus 7. Divide that by 4, and I got about 4.082. Check our answer. E to the 4 times 4.082 minus 7, and see what we get. That becomes e to about the 9.328. E to the 9.328 is about 11,248.6. So close enough. That may seem more off to you because of the numbers, but you have to remember what a giant exponent that is. That's close enough. We could have taken a lot more decimals if we wanted to get closer. So that's check. All right, that's the end of video 1. In the next video, we'll do a few more techniques.